Alright, let us look at another harmonic balance example. Let us look at this system, this one equal to 0. So it has a quadratic nonlinearity, therefore we will expect some even harmonics. However, what is the form we should use in the harmonic balance? This really is the most important question, and it is always puzzling for students more, and then as you gain experience it's a little less puzzling, but it is always a matter to be given some thought. So over here you will see that there is a second derivative with respect to time, but no first derivative. That x dot is not there. For this reason, if time t is changed to minus tau, then the d by dt of something becomes minus d by d tau of something, but because there are two derivatives, this does not change, this does not change, this does not change. That means that the solution run in reverse is also a solution. Okay, what that means is that if I have a maximum point where the slope is 0, then to the right and to the left it will be symmetrical. Let us look at this in MATLAB. You can see that this is the equation that we have. Let me clear everything here. Clear my screen. Set my error tolerance. And let me start with some initial condition of minus 0.4 or something. Okay, and then when I plot the solution, you can see that it is periodic, but you see the minimum is about minus 0.4 exactly because of this minus 0.4, but the maximum is a bit less. It is closer to 0.3. There is an asymmetry. Why is that there? It is because of this quadratic term. Let us try another solution where the initial condition is minus 0.84. And when I look at this solution, you will notice that once again this is minus 0.84 and that is 0.5. You see, I can come here and you can look closely. This is minus 0.84 exactly. Okay, but there is a bit of distortion. The maximum is smaller, but you can see that if I start over here, it is symmetrical about this line. If I have a vertical line here, it is symmetrical about that. Why is that? That is because the solution is time reversible. You look here, if I change t to minus t, the equation does not change. The second derivative does not change because there are two derivatives, minus and minus, and this of course does not change. With this understanding, I will get some insight into the solution, but before that I will just show you one last thing so that you understand what is going on. So let us try this initial condition, and you will see something a bit funnier, which is you will see a longer residence near 0. If you draw the phase portrait of this system, you will realize this is because this system has an equilibrium at x equals minus 1 and x dot equals 0. So when I am approaching that is actually a saddle. We have drawn a phase portrait of a very similar system in the past. I encourage you to draw the phase portrait of this to understand why the solution is doing this. But we will not dwell on that. And over here I will try a moderately distorted solution. You see, it is reasonably distorted, and we will look for a solution for this case. That it is distorted is clear. You can see this top is much narrower, this bottom is wider, but it is not greatly distorted. This is what we are going to look at using harmonic balance, and what we will do here is we will assume a cosine series. So what that means is that at t equal to 0, it is it has 0 slope. Okay, now because of that asymmetry, because of the shift, I have added a constant term, because this is a cosine series, right? But in Fourier series you know that there is a constant and then other things. So I have this constant term, and then I have cos omega t and something, c cos 2 omega t. Okay, so here we will start like that, and you will see that this is your check to see if the series is working. in the harmonic balance, you see constant and cosines are there. Over here also constants are there, and sorry, here these are constants and cosines are there. Okay, some cos 3 omega t has come, but we will 4 omega t has come, but we will not worry about those. We have to balance the constant, the cos omega t, and the cos 2 omega t. How many unknowns are there? A, C, P, and omega. If you are careless, you will get into trouble over here. There are 4 unknowns, but we will have 3 equations. We will have constant, cos omega t, and cos 2 omega t terms. So how we will have 3 equations and 4 unknowns. Is that reasonable? That is reasonable, because this is a conservative system. Every solution in some range, what we are interested in, every solution is a periodic solution. Therefore, the amplitude is indeterminate. You can choose the amplitude, or you can choose the time period or something, and you can find the answer. Okay, so those are our equations. We have come here now. Let us pull out our equations. Here is the cos omega t term. That's the coefficient of cos omega t. That is the coefficient of cos 2 omega t. You can't pull out the coefficient of 1. So what you do is you integrate from 0 to 2 pi over omega. And then the cos omega t, cos 2 omega t, cos 3 omega t, everything goes away. You multiply with omega by pi just to get a clean answer. This has to be 0, this has to be 0, and this has to be 0. Okay, I'm not going to use a continuation algorithm here. What I will do is I will come to the MATLAB solution. Okay, and you see I have certain number of periods. What I will do is I will do grid on, and then I will say x equals g input 2. I will come here and make this big. I'll come to this 0.5 here. That 0.5 line, I'll take the intersection with this. I hope you can see the video clearly. It is possible to do a better job of picking coordinates, but it's okay. For our purposes, this is all right now. Here is one period. Here is another period. So we have 2 periods total. I think that's good enough. Okay. So now we come here and we say t equals, and I was doing this calculation earlier. So t equals 2, 1, minus 1, 1, this minus this. That's 2 times the time period. So t equals t by 2. This is the actual time period, which means omega is equal to 2 times pi by t. That's omega, and the omega has turned out to be 0.5713. Let us come here to Maple, and what we will do is we will substitute 0.5713 in these 3 things. So I am substituting omega and finding A, P, and C. Okay, I just want 1 point, so that is what I will do here. These are 3 equations now. You see, from here to here with the comma, 1 equation. From here to here with the comma, 1 equation, and another equation. These equations have to be solved. The P is the average value. If I don't put this constraint and I just say solve, it may give some funny answer. P equals -1. That is the unstable saddle equilibrium. If I say P equals -0.9 to 0, then it gives me the 0 solution. But if I say -0.9 to -0.1, then it may give me a solution, as indeed it does. Okay, so this is 0.5713, and I am substituting that also. That is my expression. This is the solution for x. Okay, sometimes it may not give you a solution. Numerical solution using Maple has its problems. If you use Newton-Raphson, if you get a good initial guess, then it will work, otherwise it won't. Solution of nonlinear equations is, there is no guaranteed method that works in all cases. Okay, so here this is my approximation to the solution x. I come here, I already have a time, so I say x equals that. Okay, that's my solution. And then what I will do is I will plot these two, and if you look, you see that the match is not bad, right? So the time period is reasonably matching. You can see here this peak is not fully captured. Over here there is a bit of distortion. So it's not really working very well, but it is working. Okay, it is giving you an answer for something that is not very far from the singular point. It's not an unreasonable answer. So this is harmonic balance. Let us go back and now try let us make this 3 omega. Let us make this b times cos 2 times omega times t. Okay, so let's come back here, start again. Now I have 3 coefficients. Okay, combine. Now I will have let me say 1, then E3, 3, so I have 2 equations there, and this will be E4. So now I have 4 equations. That should have worked. I don't know why it's not working. Okay, that worked. Now, once again, I still have the time period. It's still 0.5713, but I will have E4 over here. I will have 4 equations, and then I will solve for A, B, C, and P, and it is giving me an answer. So this is probably a better answer, and when I substitute that, I have a new expression for X. Oops. Control X, well, Control V, that didn't work. This. Okay, so that's X. I should have done Control C. Okay, sorry for that. Here we go, X equals Control V, and I hope that this solution will be better. And you see, indeed it is. So this is how harmonic balance works. When you have more and more equations, it may not always work. You may not always be sure which is the most appropriate form to use. Sometimes you will use a numerical continuation method to find solutions as some other parameter is varied. In this case, just to show you that the method works, I indicated what the form is. I pointed out that you have one indeterminacy. So when you look for a specific solution, in this case, the time period matches exactly because I have used the time period that matches the numerical solution. Okay, so this ends my demonstration of the method of harmonic balance for a few systems. I will give you an assignment with something else in it.